Welcome to Future Epoch, where we learn more about our world. For as long as humans have imagined the future, we have imagined ourselves in it, mechanical, perfected, and tireless. That dream has appeared in science fiction, on laboratory floors, and now in real factories, shipping facilities, and research campuses around the world. But something has changed. The humanoid robot is no longer a concept. It is arriving, imperfectly and uncertainly, into the real economy. And what happens next may reshape how work itself is defined. A humanoid robot is, by definition, a robot that resembles the human body in shape and function. It typically has a head, a torso, 2 arms and 2 legs. It is designed to operate in spaces and with tools built for human beings. That distinction matters enormously, because most existing automation, the robotic arms in car factories, the sorting machines in warehouse logistics, is purpose-built for a specific task in a controlled environment. Humanoid robots are being built to do anything, anywhere, in environments that were never designed with robots in mind. That is an extraordinarily difficult engineering problem, and it is the central bet that dozens of companies are now making. The reason that bet is being made now, and not 10 years ago, is the rapid maturation of artificial intelligence. Language models, computer vision systems, and reinforcement learning algorithms have reached a point where machines can perceive, reason about, and respond to unstructured environments at a level that was not previously achievable. The hardware has also improved. Battery technology, actuator design, and sensor miniaturization have all advanced substantially. The result is a convergence that is pulling humanoid robotics out of research laboratories and into commercial investment at a pace that has surprised even many insiders. The intellectual ancestry of the humanoid robot stretches back decades. Honda began internal research into bipedal locomotion in 1986, believing that a robot genuinely useful to people should be able to navigate the environments people actually live and work in. That project eventually produced Asimo, unveiled in the year 2000. Asimo could walk, climb stairs, and recognize faces, remarkable achievements at the time, but it remained a demonstration platform rather than a practical machine, spending most of its life performing at exhibitions and press events. The field shifted more dramatically in 2013 when DARPA launched its Robotics Challenge, a competition designed to push machines toward real disaster response tasks. Teams were required to solve problems that controlled laboratory environments had historically allowed them to avoid, opening doors, driving vehicles, climbing over rubble, and operating hand tools in unpredictable conditions. Boston Dynamics entered with Atlas, a hydraulically powered humanoid that could navigate rough terrain with an agility that drew global attention. Atlas fell down frequently in early competition footage, and those failures were instructive in their own right. The world could see, in real time, how hard the problem actually was. Over the following years, Boston Dynamics refined Atlas through a series of increasingly striking public demonstrations. By 2016, footage of Atlas recovering from being shoved, walking through snow, and lifting boxes onto shelves had reached hundreds of millions of viewers. The videos were startling not simply because of what the robot could do, but because of how it moved. Atlas moved like something alive. By the early 2020s, the landscape had changed again. Tesla announced its Optimus robot project at an AI Day event in 2021, framing the machine explicitly as a replacement for repetitive and dangerous human labor. The first functional Optimus prototype appeared in 2022. Figure AI, founded that same year, attracted a single investment round of $675 million in early 2024 from Microsoft, OpenAI, NVIDIA, and Jeff Bezos. Sanctuary AI, a Canadian company, has been developing its Phoenix robot with a focus on general-purpose manipulation in commercial settings. Agility Robotics, backed by Amazon, has been deploying its Digit robot in warehouse operations. And Boston Dynamics itself released a new, fully electric version of Atlas in 2024, retiring the hydraulic system that had defined the platform for more than a decade. The pace of development, and the scale of capital flowing into it has no recent precedent in the history of robotics. The central problem facing every humanoid robot company is the gap between demonstration and deployment. A robot can be trained to perform a specific task with considerable reliability in a controlled setting, and then fail repeatedly when that setting changes in small, unpredictable ways. The real world does not behave like a laboratory. Objects shift position. Lighting conditions vary. Floors are wet, uneven, or covered in debris. Instructions are ambiguous. The sheer variety of situations a human worker encounters in a single shift represents a combinatorial challenge that no deployed robot system has yet solved at scale. This gap has a name in the field: the generalization problem. Teaching a robot to do one thing well is achievable. Teaching a robot to do anything adequately, in any environment without task-specific programming, remains one of the hardest open problems in artificial intelligence and robotics combined. There is also a physical challenge that receives less public attention than it deserves: dexterous manipulation. Human hands are extraordinarily capable instruments, and much of what makes human labor valuable is the ability to handle objects of varying size, weight, fragility, and shape without prior instruction. Replicating that capability in a mechanical hand remains technically demanding, expensive, and prone to failure in ways that make sustained real-world deployment difficult. Then, there is the question of economics. The most capable humanoid robots currently cost hundreds of thousands of dollars per unit. For that price to make sense to a business, a robot would need to reliably perform a broad range of tasks across long operational shifts without constant human supervision or maintenance. No commercially deployed system has yet crossed that threshold, and the companies building toward it are working against significant uncertainty about when or whether the unit's economics will close. If the generalization problem is solved, or even partially solved, the consequences are difficult to fully anticipate. Major financial institutions have projected humanoid robot markets worth tens of billions of dollars by the early 2030s, with some long-range estimates reaching into the hundreds of billions within 2 decades. Those projections are speculative, and the history of robotics is littered with forecasts that fail to materialize on schedule, but they reflect the scale of what the investment community believes could be at stake. The most immediate application is manufacturing, particularly in sectors where automation has historically struggled: final assembly in consumer electronics, food processing and packaging, and logistics operations involving irregular or fragile items. Tesla has indicated it intends to deploy Optimus robots within its own factories, a move that would simultaneously be a live test of the technology and a sustained demonstration of its commercial potential. The longer-term implications extend into labor economics. A sufficiently capable humanoid robot would represent a form of labor that does not require wages, benefits, rest periods, or supervision in the conventional sense. For businesses operating in tight-margin environments with persistent labor shortages, that proposition is deeply attractive. For the workers those robots would displace, it represents a structural threat to employment in sectors that already employ hundreds of millions of people globally. The political and social questions that follow are not yet being answered at the pace at which the technology is advancing. What happens to workers displaced by general-purpose robotic labor? Who captures the productivity gains? How are the legal frameworks around workplace safety and liability applied to a machine that makes autonomous decisions? These are not hypothetical concerns. They are practical questions that regulators, businesses, and workers will need to answer, and the window for deliberate engagement with them is narrowing. The humanoid robot story is not simply a technology story. It is a story about what human labor means, and what happens when a machine can perform that labor without being human. The most important thing to understand is that this is no longer a question of whether general-purpose humanoid robots will become technically viable. The question is, when, at what cost, and for whom the benefits of that viability will flow. The companies building these systems are solving engineering problems, not social ones. The social arguments will have to be made, and contested, by everyone else. Decades of science fiction told us that when robots arrived, we would recognize the moment clearly. There would be a reveal, a demonstration, a crossing of some obvious threshold that everyone could point to. The reality is less dramatic and more unsettling. The threshold is being crossed gradually in warehouses and research facilities and quarterly earnings calls through incremental improvements in actuators and training data and inference speed. Each step looks modest in isolation. The aggregate is not modest at all. The question is not whether machines will enter human workplaces at scale. The evidence suggests they will. The question is what kind of world we intend to build around that fact, and whether we will begin that conversation in earnest before the machines are already there. Thank you for watching. If you've enjoyed this content and want to see more, please consider liking the video and subscribing to the channel.